I ground it here. We'll call this inversion 1. I could also take the 4-bar, ground it over here. Yep. And that would be the second inversion. I could also take the 4-bar, ground it on top here. And that would be the third inversions. And the fourth is grounding the right link. So what we're going to do with the vice grip look at how to solve 3 out of 4 inversions. The fourth version, the fourth inversion. Too difficult to solve. So what I'm going to do is I'm going to do the vice grip 3 different ways, and for your convenience, I actually printed out a copy of the vice grip homework. Okay? That you can, perhaps, if you want to, draw on this while I'm sketching this thing out. All right. So I'm going to follow the steps on this that I outlined. So what I'm going to do is first let me, on this one here, this is the easiest way if you had to choose your own, or not, you had to, if you were allowed to choose your own ground, your own inversion on this, I want you to look at a couple things. So first, let's look at the vice grips, all right? Okay. The first thing I want you to notice about a vice grip, a pair of vice grips, is that it is a 4-bar mechanism. You have 1, 2, 3, 4 links here. Okay? Now you may look at this, say, but you're moving this thing here, and is that really a revolute joint? You're correct, it's not. It's actually kind of a roll slide, but we're going to model it as a revolute joint. Okay? So we got a pin joint here, 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 and here. And I want you to notice, so when you take this thing, if you take this thing here, notice when it's clamped down, notice when you clamp it down, that this link here and this link here are collinear. That's no coincidence. Thank you. All right. Remember the other day where I was on the leg press machine and I just took that leg press and I just locked my leg like that? That's what the vice grip is doing here. So when you look at a mechanism, and you say, how can I get the greatest mechanical advantage out of this mechanism? Just think of what's the configuration where two links, moving links, become simultaneously collinear. And that's when you have your greatest force out. Okay? In theory, you can have infinite force here, but really you can't because these things will bust. These pins will bust. All right? So I'm going to hand out the vice grip. So remember I told you I worked in the oil fields, we had plenty of time, and we had these tools, and so we had vice grip wars.
Maybe clamp it.
So you go like that. To beat that. All right. Don't hurt yourself. So on this one here, what I'm going to do is I'm going to look at the first inversion, and I'm going to ground this link right here.
There you go.
All right. So I'm going to call this link 1. This is 2, 3, and 4. Now the reason why this is the easiest one is notice that there's a force on this thing here, where your hand is squeezing the thing, and there's an output force here. Well, like I said, if you have the choice of choosing the ground on a mechanical advantage problem, you choose a ground location that has the most forces acting on it. Well, let's look at link 2. There's no external forces on link 2. There's one external force on link 3. Link 4, there's one external force. But this link here, there are actually two external forces. So that's the most judicious link of this mechanism to select as your ground. So this is the easiest way to solve this problem. We're going to do that one first. So once you select your ground, you have to, step 1 here is to identify your input link and your output link. So on this one, excuse me, on this one here, what should my input link be? In equals what? Yep, 3. And out should be what? 4. Okay. So that's the major step right there, is choosing what your input link is and what your output link is. So the next step says find the velocity of VI in L. So what I'm going to do here is find the velocity of I, 3, 4. Okay? And that velocity in this case here is omega 3 times I, 1, 3, I, 3, 4, which equals omega 4 times I, 1, 4, I, 3, 4. And then I'm going to find that velocity ratio. All right. Now, getting ahead of ourselves a little bit, if I have, so if I need to find the instant centers on this, because I have I13 and 3,4 defined. So this is I12. This is I14. I34. So this is the velocity that I'm interested in looking at. And this is I23. Excuse me. So this right here, when I look at this, this is I13. All right. So think of I13 as this instant ground. So let me draw it like this here. And let's just focus on link 3 here. So if I'm moving this thing like this, what is omega-3? Is omega-3 positive or negative rotated about I-13? Just look at this. So looking at that, I see that I have a positive omega-3. Now, if omega-3 is positive here, what direction is I34 moving? Is it moving down, up, left, or right? What direction is I34 moving? You're pinned it here, you're looking at this, omega-3 is going like that, so what direction is I34 moving? Right. So it's moving like this. Okay? So if I34 is moving like that, and 3,4 means that it belongs to link 3 and 4 simultaneously. Now 4 is moving pinned, or moving about this pin joint I14. What direction is omega-4? Is it positive or negative? It's negative. So omega-4 is negative. And that's why you look at the velocity of your I34 in order to determine your omegas. Okay? So I have a negative omega-4. So let's continue. Now that we've taken care of that, it says, step 3, draw a line of action for input forces. So let me go ahead and do that. So here's my input force here. And what I do on this here is it says the input forces direction is from the outside world towards the mechanism. So that means that I'm coming from the outside world towards the mechanism. All right. I do the same thing on the output forces. So on the output forces, let me draw my line of action. So that's on right here, okay, where BB is. That's that line of action. And it says that it's from the mechanism towards the outside world. So this one here is drawn like so. All right. Now the direction of these things determines your moment, whether it's negative or positive. So that's why this step is rather important to make sure the directions are right. Now it says to draw the radial moment arms for the input forces from I1 in to the perpendicular of the respective line of action of the force. So here's I1 in, which is I13. So what I do is, let me get my big ruler for this. I move along the line of action of the input force until it strikes the ground there. So this right here is, this distance here is R in.
So are the two lines of action perpendicular?
These right here.
Yeah, F in and F out.
This line of action here is given to you by looking at this.
Right. Remember? Yeah. So how did you know? You said you moved along the lines. How did you know, like?
So what I did is, because the problem statement gave me this here, I just drew this line here bigger. And then I took my ruler and moved along here until I saw where my ruler went through I13.
I get it.
Okay? Yeah.
I'm sorry, can you just go over one more time how omega-4 is negative?
Yep. So first of all, I look at, I'll show you a couple of things. First of all, I look at the input. Because my hand is pushing down on this thing here is moving like that about I13. So therefore, I have a positive omega-3. This I34 belongs to link 3. If omega-3 is like this, moving about this center, then this thing here moves out like this, perpendicular to this line here. You see that? Okay. So now, let's look at link 4. I34 also belongs to link 4. Link 4 is pinned about I14. So to have this velocity go this way, because we already know that it does that, omega 4 has to be going like that. Now, so that's one way of looking at it.
I was thinking about it being pinned to I13, that's why I was
Okay,
asking that.
so the other way of looking at it is that we know this jaw needs to move down, or we suspect that it needs to move down in order to clamp on that beam. And so therefore, omega 4, in order to clamp down on that, has to be negative.
Thank you.
All right, but the velocity of I34 is a better way to define it. Okay.